Okay, so we are now recording. It's a great pleasure to have Gia Dvali present today's virtual seminar. He's going to tell us about the S-matrix exclusion of de Sitter and its consequences, which should prove very stimulating. And thanks a million for joining us, Gia.
Thank you very much for the invitation. It's a great pleasure to give this seminar. Of course, I consider this as a sort of an informal seminar, so you can interrupt me anytime, ask questions and stuff. So yeah, as I will talk about de Sitter and what kind of constraints we get on de Sitter from an S-matrix and the microscopic theory. And will be mostly based on these talks, on these papers. The original one, the original papers written in collaboration with Cesar Gomez, and later with Cesar Gomez and Sebastian Zell. And so this paper is the most recent one that puts a certain perspective on this. Okay. So some notations. Let me use. So I will use notation for vacuum energy density, lambda. So lambda will have dimensionality of course, I will use particle physics units when speed of light and Planck's constant is equal to 1. And lambda will have dimensionality of mass to the fourth. It's an energy density, cosmological constant. Newton's gravitational coupling will be G. Planck mass, as usual, will be m Planck, which is the inverse square root from G Newton. And the gravitational radius, actually for both de Sitter and the black hole, I will denote by R. So for de Sitter, gravitational radius, or sometimes it's called Hubble radius, is given by lambda times G Newton. I mean, the gravitational inverse gravitational radius square. So then I will have several numbers. And so specifically NSP will denote number of particle species in the theory. For example, if you are working with D-branes, it will denote number of Champatton species and so on, open strings species and so on. So in case when I discuss string theory, it will be G string, it will be string coupling, and this is dimensionless string coupling, and string scale will be the M string. Okay. Now everybody, of course, de Sitter is an extremely familiar space for everyone. So here, in particular, in a particular slicing. So this is a specific. You can think of it as a specific case of Friedman, Lemaitre, Robertson, Walker universe, where A is the scale factor, and de Sitter in this slicing would correspond to the exponentially expanding scale factor with constant R, where R is the curvature radius, which I just introduced, and the 1 over R square is equal to lambda divided by m Planck square. Okay, so now, of course, most of the discussion about de Sitter space is within semi-classical context. Semi-classical, I mean, in the context where you treat the de Sitter background as something rigid and God-given, and you discuss physics on top of this de Sitter background, de Sitter geometry. And so semi-classically, what are the features of de Sitter? So an observer, so this is Alice, observer in de Sitter. So Alice sees horizon, she's surrounded by horizon. And there is so-called Gibbons-Hawking radiation. So constantly a particle creation takes place in de Sitter space. This is a quantum process, intrinsically quantum process. It has an approximately thermal spectrum. Actually, semi-classically, it has exactly thermal spectrum with temperature 1 over R. Now, this is highly schematic, this picture. You should not think that radiation is somehow coming necessarily from the horizon towards us, because this is a quantum process, and the wavelength of the created particle is of the same size as the horizon. So you cannot really say that it's point-like. The particle is not really point-like. And de Sitter also has entropy, the famous entropy, so Gibbons-Hawking entropy. This entropy is pretty similar to black hole entropy because it scales as area in Planck units. Okay, so this horizon area in Planck units. Now, why is de Sitter important? Because it plays very important role in cosmology, both in early cosmology, de Sitter-like states, not exact de Sitter. Of course, exact de Sitter semi-classically is eternal. It's an eternal space, a future eternal, not past eternal, by the way. Shown by people like Guth, Vilenkin, it's not past eternal, but it's future eternal, semi-classically. Now, the Sitter-like state describes a phase. It's commonly accepted. The current sort of cosmological model is the model of inflation. So we come from the Sitter type epoch back in the past. Okay, and also current observations indicate that we're re-entering in the Sitter type epoch now because of so-called dark energy. That is, we are postulating dark energy because it looks like we're entering again in the exponentially expanding, accelerating phase with much of curvature radius. So it is absolutely crucial to understand physical properties of the Sitter space because of this importance for our cosmology. Now, this also creates a puzzle. You probably heard many times about this puzzle. Sometimes it's called cosmological constant puzzle, because in order to get the Sitter space, because the lambda, the cosmological constant that is a source for the Sitter space, is sensitive, quantum mechanically sensitive to the cutoff of the theory. Okay. And so there is this puzzle why lambda is small, which is a separate story. So now the question is, what does quantum gravity has to say about de Sitter? And one of the messages of this talk that I will argue is that in the quantum gravity, such as, quantum gravity and string theory, in particular string theory, in fact, any S-matrix formulation of quantum gravity, and that's the only formulation we currently really have, excludes de Sitter vacua, both for stable and data stable. So it simply excludes de Sitter, which means that the question why lambda is small is not a question of naturalness, but it's a consistency issue. It's like anomaly cancellation. So the theory just tells you that you cannot have lambda, which would give rise to de Sitter. It has to be a positive cosmological constant is excluded. Also, what is excluded is any de Sitter like future eternity. Okay. And so, of course, it's a little bit profound story, and S-matrix plays a fundamental role in this story. Now, in current formulation of quantum gravity, in particular in string theory, okay. So you can. So I will. For listening to this talk, the knowledge of string theory is not required, but I will go in part. So if you want to think in terms of effective field theory about quantum gravity, that's perfectly fine. You don't need to know string theory, but I will make parallels and comparisons with string theory, because string theory actually is based on S-matrix formulation. Actually, any formulation of quantum gravity that we, as I said, that we understand is based on S-matrix formulation. So S-matrix is not just a computational tool for quantum gravity, but it's a formulation of the theory. Now, there are certain necessary conditions that we have to obey to formulate for this formulation. And one is that you need globally defined time in order to formulate S-matrix. Now, this is, of course, absent already in classical de Sitter. And the second thing we need is an S-matrix vacuum. Okay. Now, what do I mean under this is the following. Because, okay, we can say, all right, let's imagine for a moment that we are really entering in de Sitter, eternal de Sitter phase, okay? Okay, imagine that the cosmological constant, imagine that there is a positive cosmological constant, tiny cosmological constant, and our universe is entering into a de Sitter state, okay? And now you can say, what's the problem? After all, okay, we don't have a globally defined time, but we can still define time on the time scales shorter than the Hubble radius r. And on those time scales, we should be able to formulate an effective S matrix. Okay. After all, if I do experiments at LHC, I do S matrix computations. So why should I worry about horizon somewhere 10 to the 14 billion light years away or something? Okay. But actually, that's not true, because there is a discontinuity basically in the theory. And again, I'm making this parallel with anomaly cancellation, because you need exact zero. Now, the reason here is that for S matrix formulation, even if you attempt to have an effective S matrix formulation on short time scales, you still need a vacuum state. So you need to define in states and out states and the vacuum. And now the necessary condition that the vacuum has to obey is that it should not be able to recoil and absorb information. In other words, vacuum should be absolutely rigid, because otherwise, every time you have to define, let's say you have some in states, you define those on some vacuum, but then during the scattering process, vacuum absorbs some information and recoils. And then every time you have to define out states, because out states you have to define on the vacuum, there's excited states on the vacuum. This will depend on the scattering process, and that makes it impossible to define S matrix. So this is very important. Now, there is actually a unique limit in which de Sitter can become a rigid vacuum. There is such a limit. You can take such a limit. For this, what you need, in other words, there is a limit in which it doesn't recoil and becomes really God-given external geometry. Now, for this, what you need is that you need to take gravitational constant to 0, so which means Planck scale to infinity. So you decouple gravity, but simultaneously want to keep geometry fixed. And simultaneously, you have to take cosmological constant to infinity. So there is a double scaling limit in which you keep the Hubble radius finite. In this limit, indeed, de Sitter becomes a rigid vacuum. Okay, but there is a problem. The problem is that quantum gravitational coupling, okay? In other words, quantum coupling among gravitons, this is graviton-graviton coupling, also depends on the Planck scale. So the quantum coupling among gravitons is given by momentum transfer square divided by Planck square, or Newton's constant divided by the de Broglie wavelength of momentum transfer in the process. And you can see that in exactly the same limit in which you make de Sitter a rigid vacuum, graviton S matrix becomes trivial. So quantum gravity becomes trivial. Okay, so that's the price to pay. The same is true in string theory. Okay, you can see this explicitly in string theory. Again, as I said, for those of you that is familiar with string theory, you know that in string theory, gravity is embedded. Einstein gravity is embedded in string theory. I mean, the quantum version of Einstein gravity is embedded in string theory as a vibration, lowest vibration of a closed string. So closed string vibrates, and it has a spin, massless spin 2 vibration, and that's graviton. And so gravitational S matrix is embedded into closed string S matrix in string theory. And it's the same is true. So exactly the same is true, because you can see that in the rigid limit, you can translate gravitational coupling in terms of string scale and string coupling. And no matter what you do, you have to take string coupling to 0. So the closed string S matrix becomes trivial. The story with open strings is a little bit more subtle, but the closed string is the part of gravity. And this is very important because what we see that the de Sitter is really sensitive to quantum gravitational part. Now, you can make this more explicit just to see the scaling. Just an example. Now, we can try to create the de Sitter type state in string theory by using positive tension of d-branes. So this was suggested long ago in these papers, and that's usually the source of positive energy construction, de Sitter-like constructions in string theory. And you can see immediately why this the S-matrix formulation makes this problematic, because, for example, we can take example directly in 10 dimensions. In 10 dimensions, you can try to generate. So in 10 dimensions, the d-branes are these objects that are soliton-like objects that exist in string theory. They have positive tension. And now, in 10 dimensions, you have these d-branes, which are 9 branes, which are space filling. So basically, they fill the space. So basically, their tension acts like a cosmological constant in 10 dimensions. So you can put on top of each other branes and anti-branes, many of them, n of those, and you will create effectively a cosmological constant-like source. Okay. Now, this source at the end of the day is unstable, but that's not important for this discussion. So you can think of it like a hill that you are creating in this construction. Okay, so now we are putting system on top of the hill, right? And classically, you can get the Sitter there. Okay, but again, you can see what this requires. And this double scaling limit, you see explicitly that it's the limit where necessarily G string should go to 0. Okay. Now, notice the following, that let's come back to again to effective field theory description. So notice the following, that there is no problem of defining S-matrix for other interactions. For example, I can take this rigid limit, I can take Planck scale to infinity, and I can define S-matrix for example, QCD, not for any theory which has Wilsonian ultraviolet completion. No problem. The I can have non-trivial S-matrix. So the issue is really quantum gravitational. So de Sitter, whenever we treat de Sitter as a vacuum, quantum gravity decouples. But that cannot be, because quantum gravity is coupled because Planck is finite, and string coupling in string theory is finite. And this is the issue. There are also clear signals of the inconsistency of S-matrix already for finite and Planck. You can see very easily that if you want to define an effective S-matrix in de Sitter for finite and Planck, for example, graviton scattering with center of mass energy comparable to this number, and Planck squared times R, cannot be described. Okay. Okay. So now the question is, there are two questions: what to do? Okay. So this matrix tells us that de Sitter we cannot treat as a vacuum. Period. So there are two questions. First, what to do? How to treat de Sitter? Okay. And secondly, how is the S-matrix constraint enforced microscopically? Okay, because, for example, imagine that we don't pay attention to what theory tells us, and we move and we say, okay, let me postulate anyway that there is a de Sitter type state in quantum gravity. The theory is much smarter than we are, so theory will tell us what is wrong that we're doing something wrong. Okay, and this is what I want to explain. Now, this lets us, so in other words, what I want to say is that the S-matrix constraint on de Sitter imposes upon us a corpuscular picture of de Sitter. Why? Because if de Sitter is not a vacuum, so in S-matrix theory, we only have vacua and excited states on top of the vacua. Okay. Now, if de Sitter is not a vacuum, then it has to be an excited state constructed on top of a valid S-matrix vacuum, such as Minkowski. So therefore, we need to treat de Sitter as a state constructed on top of the vacuum. Now, the state that you can choose to be maximally classical is coherent state. So I will discuss coherent state, but there are other possibilities also. Now, whatever the choice of this state is, you choose this state in such a way that the expectation values over this state, at least at the initial times, at some initial time, they reproduce classical de Sitter. Okay, classical de Sitter metric. All right. So this is the story, right? Now, this gives, of course, what I'm just describing gives a new concept in cosmology or in treating de Sitter in particular, which we call corpuscular completion, corpuscular resolution, and this is very important to sort of spell very clearly because you see in standard GR, if we think in terms of classical GR. In classical GR, you could say, oh, there is not much difference between de Sitter or a Minkowski or any other background. So, for example, Minkowski is one out of infinitely many possible backgrounds in general theory of relativity. So, but S matrix tells us that Minkowski is special. Yeah, and de Sitter, therefore, it has to be visualized as an excited state on top of Minkowski. And therefore, de Sitter has to be resolved corpuscularly. Now, there are certain universal properties that come with this corpuscular resolution. And it's very interesting that the number of constituents always comes out to be equal to the inverse of their gravitational coupling. You can check this. I will not do this in this talk, but it's straightforward to check. And their frequencies are not surprisingly given by the Hubble. Okay. So we get the following relation that the couplings are given by 1 over n, okay, and 1 over entropy. Now, such states actually we call saturated states. So saturated states. This tells us that de Sitter is an example of a saturated state, saturated critical state. So in other words, state for which the number of constituents is given by the inverse coupling of those constituents, inverse quantum coupling of those constituents, and is equal to the entropy, as you can see very clearly from here. And this has very extremely important consequences. Okay. So these consequences will come a little bit later, but before that, of course, now we have a corpuscular picture of de Sitter. A corpuscular picture in certain approximation must reproduce semi-classical story, of course. Now, semi-classically, we had Gibbons-Hawking radiation in de Sitter space. And we thought that Gibbons-Hawking radiation was a vacuum process because we were treating de Sitter as a vacuum in semi-classical story. But now we know that this matrix is telling us that de Sitter cannot be a vacuum. It's a coherent state constructed on top of Minkowski vacuum. So Gibbons-Hawking radiation is coming as a literally decay, depletion of this coherent state. And you can see that at the initial times, it's a Hamiltonian process. In other words, it's a Hamiltonian process of a depletion. Literally, the Sitter coherent state decays, and the Gibbons-Hawking radiation is a result of this decay. And at initial times, you indeed get emission rate reproduces Gibbons-Hawking rate, and the spectrum is approximately thermal. But this is only true at initial times. Now, in semi-classical picture, this is true always. Why? Because in semi-classical picture, it effectively corresponds to taking n to infinity. So therefore, you have de Sitter acts there like an infinite capacity reservoir, and so this is eternal. But not in quantum picture. So in quantum picture, de Sitter ages. It has an internal clock because it loses constituents. Now, this.
Sorry.
Yes, of course. Sure.
This picture reminds me of what's going on in Rindler.
It was very similar. Rindler also, if you resolve it corpuscularly, is very similar, exactly. So in other words, first of all, the particle creation process is not only exclusively characteristic of de Sitter. You are absolutely right. That also happens in Rindler. It also happens for a black hole. And Rindler is essentially a near horizon geometry of a black hole is like Rindler. Exactly. So in other words, what we are discovering is the following: that the moment you try to understand, and I will discuss precisely that for black holes later, the moment we try to understand corpuscularly the space-times with horizons, they come out to be saturated states. And so the particle creation, for example, in Rindler space, I can also understand as depletion of a coherent state that describes Rindler, okay? So that's a very, very absolutely correct question. And the answer is yes. That's exactly the same reason also in Rindler. Now, this decay has, now I want to explain the story with the quantum clock, okay? This decay is, of course, democratic in species. So suppose you have different number of particle species, okay, in the theory, which we do. For example, in the standard model, we have approximately over 100 species. In string theory, you have many species, jump atom factors, etc., etc. So decay is democratic in species, and you can see why. So in other words, in semi-classically, you produce species democratically because it's a thermal story, and thermality implies democracy in species. But here we see explicitly why this particle production is democratic in species, because gravitational interaction is democratic in species. So at the initial times, you again produce species democratically. Now what happens? Let's take this transition process, okay? Now, again, this process is highly schematic, but it captures the essence. Why? Because, of course, there are many different processes, not only 2 to 2, but there are plenty of other processes. But the essence of the process is the following. Okay, let me consider this process in which I emit a quantum J out of de Sitter. Okay, and then I have the state, final state. Okay, so in this one particle emission process, let's consider. So initial state I will denote by n. The final state I'm denoting by n-1. Again, this is highly schematic because there is no such thing as particle number conservation, obviously, in relativistic theory. n-1 I put here in order to distinguish from n. And there is also index j. Why index j? Because the state is entangled, obviously. As a process of particle creation, the state is entangled. And here comes a very important novelty that is revealed by corpuscular theory, that is absent in semi-classical theory, and that is also true for black holes, which I will discuss in a little bit later. Okay, the point is the following: that not only J state is entangled with n-1J states, but n-1J states, in other words, what remains out of de Sitter is also self-entangled. There is an inner entanglement, because de Sitter has constituents. And so what happens as a result of this process, what remains, they become entangled, more and more entangled with time, okay? So what happens is that on one hand, de Sitter loses constituents, okay? And on the other hand, what remains is more and more entangled, okay? So there is this inner self-entanglement that is gross. And it reaches maximum after a certain time scale, okay, which is, we call quantum break time. Why quantum break time? Because beyond the time scale, there is absolutely no way to describe what remains out of de Sitter as any sensible semi-classical state, okay? Simply, there is it just simply becomes intrinsically quantum. Now, this time scale, of course, is extremely important, okay? And it's given by this expression, okay? And of course, and the number of species increases the rate, and so it makes this quantum break time shorter. Now, this quantum breaking time is a generic feature of saturated states, okay? And this is very important because, so the ordinary, you see what happens is this, right? So if we consider a macroscopic object, I don't know, a planet, for instance, or something else, or this chair, for instance, right? I mean, there is always some departure from classicality because of quantum effects, because of rescattering, etc., etc. But this departure usually is not significant. Okay, what is special about saturated objects is that saturated systems is that they fully quantum break. In other words, after time TQ given by this general formula, and this is an extremely important formula, one of the most important formulas in this talk. So the quantum break time is given by classical time of your system. For example, for de Sitter, this is Hubble, divided by the quantum coupling multiplied by the number of species that experience this quantum coupling. Whatever the quantum coupling is, okay? So after this time scale, there is a complete departure between classical and quantum evolutions. And we call this quantum breaking. Now, it's very important to understand that quantum breaking is not some sort of instability or anything like that. No, it's just simply departure from classical evolution. And for de Sitter, this is a disaster because de Sitter is there in the first place because it had a classical source. And now it has its own quantum evolution, which completely departs from what classical source is trying to tell it. So for de Sitter, the classical time is Hubble, and then alpha is gravitational coupling constant. If we are considering pure de Sitter with pure gravity, okay, so then we'll recover this expression for de Sitter. But the expression, as I said, is much more general. So if you have your favorite theory, which somehow does something in de Sitter, for example, inflationary theory or whatever, this will be quantum breaking time given by the appropriate coupling constant. So for example, in case of D branes, you can see immediately what happens, that the role of number of species is played by the Champaton factors. Champaton factors are the factors of open strings that are stretched between D branes. And so the quantum break time for generic string de Sitter is given by this. Okay. So for generic string de Sitter, if you have some construction, okay, now you can actually, this formula is more general than this construction. So if you have some construction in string theory, okay, so somebody told you that there is some construction in string theory, let's say, and there is a stable de Sitter. Okay, of course, de Sitter has curvature radius R. So you can see immediately that this must be the quantum break time. The latest after this time scale, the system quantum breaks. Again, this is not an instability. It's very important to understand. This is an inconsistency, not an instability in the case of de Sitter. Now, I will discuss the generation of entanglement in more details in a moment. Okay. But before, so I will reiterate this later, so you don't need to pay attention to this. But the second part is the following.
Sorry, I'm a little confused as to why it isn't an instability, because you have not set up an eternal de Sitter. You have presumably prepared a state at early time, which is built from this coherent state, and you're evolving that. So it looks more like an instability the way you formulate it to me.
No, not really. Why does it look like it's a bit?
Because you're not dealing with an de Sitter has a symmetry. It's maximally symmetric.
Yeah.
Time translation.
Right. That's right. So you break it.
Whereas your formulation doesn't look like it has that formula.
You mean no? Yeah. If you define instability in that way, but that I would not. Yeah. Okay. So I would not call that instability. I mean, this is a time evolution. This is a time evolution, which, for example, instability I would call something that has Lyapunov exponent or a tachyonic mod in it or something like that. But if you define,
okay, then I understand.
Yeah. If you define instability in your way, then fine. That would be this particular type of instability. But however, I would avoid. I would try to avoid calling this an instability precisely because system can do this without ever becoming essentially tachyonic. Okay, so that is the key point. Okay.
Sure, I understand. Yeah.
Right. Now, actually, there is another case where precisely your question is here. So, for example, what we've discovered in this paper with my collaborators. So what we discovered is that for the systems which classically have Lyapunov exponent, Okay, so if you have a system which classically exhibits Lyapunov exponent, then quantum breaking time can be much shorter. Okay, so quantum breaking time can be logarithmic. Okay, but as I said, this is an absolute bound for the other one. This is an absolute bound, this one, irrespectively whether you have Lyapunov exponent or not in your system. Okay. So now let's try to understand what are the consequences of this. And the consequences are, of course, extremely important, because what we are learning is that de Sitter, after time TQ, quantum mechanically is doing something incompatible with the classical geometry or classical evolution, because we created de Sitter in the first place by introducing lambda, okay? And lambda wants de Sitter to be classical, okay? It wants expectation. Of course, there is nothing classical in the universe, but since lambda is a classical source, it wants de Sitter expectation values of the operators to behave classically, the way classical equations tell them. But they don't behave classically. They behave after TQ, they completely go out of control, and there is an inconsistency. So this excludes any sort of situation which lasts longer, any de Sitter which lasts classically longer than TQ. So if you have a theory of de Sitter which lasts longer, which classically lasts longer than TQ, then this theory tells us that we will going to run in contradiction. So the consistent de Sitter-like states would be the ones that classically or by some other means find graceful exit after the time scale that is less than quantum break time, less or of order, okay, or equal. And this excludes any sort of metastability. And also, this has important consequences for inflation, because it tells us that the number of e-foldings that inflation has is limited. Now, what is very interesting is that now the quantum theory tells us that there is an absolute maximal duration during which inflation could classically have lasted. And during this time, there is a quantum clock that is internally there, which gives departure from semi-classical evolution. And this quantum clock imprints intrinsically quantum gravitational perturbations, for instance, in the universe, and quantum gravitational tilt, and so on. And the strength of this is given by this ratio. The strength of this is given by the exit time divided by the quantum break time, okay? All right? And so it's enhanced by the number of species. And this is very interesting, because this means that if you have a theory with large number of particle species, the quantum gravitational effects can be the dominant ones, okay? Now, let me mention a couple of words about species. Now, when should we finish? Can you tell me when we move to the discussion, so that I normalize?
It depends really on questions, but we prefer you to go through to the end, but the normal is roughly an hour 15 minutes.
Oh, yeah, hour. Yeah, no, that's plenty. So that's perfectly fine. Thank you. Sure. So now let me tell you a couple of, before I go. So now I structure the rest of the discussion like this. First, I will discuss why species do this, why species magnify quantum gravity effects. And then I will discuss entanglement, generation of entanglement and Page's curve for de Sitter and black holes, okay? Compare with each other. So from this expression, we see that actually quantum gravitational imprints, for example, coming from inflation, they are enhanced by number of species. And that's generic property of species, okay? Now, species have this universal effect, and this is completely non-perturbative. It has nothing to do with perturbation theory or renormalization. That species enhance quantum gravitational effects. In particular, species lower the scale at which quantum gravity becomes strong. Okay, and this is a universal bound coming from several arguments, many different arguments. I will present only two because that's sufficient. So in other words, suppose you have a theory in which you have Planck scale and Planck. Now, Planck scale has been measured. We measure it in laboratory because that's a inverse square root from Newton's constant. So Planck scale is there what it is. And also, we know that in the theory, we have NSP, number of particle species. Okay, these particle species may belong to a hidden sector, may interact with the standard model, doesn't matter. So there is total number of particle species. Then the bound tells us that the latest where we should encounter strong gravitational effects, scale m star, is not Planck scale, but is lowered by the square root of n species. Now, let me give you the argument that I like most is the most transparent one and the simplest one, and it's a fully non-perturbative. Comes from black holes. Okay, black holes, they evaporate thermally to the good approximation. Okay, so again, the same story there. In the limit in which we are in semi-classical gravity, a black hole approximation is thermal. So it's similar to Gibbons-Hawking radiation or in de Sitter. So it's thermal. Now, departure from thermality. So now taking the standard equations for black hole evaporation, so the Hawking formulas, standard, you can immediately derive this equation. Why is this equation important? Because the left-hand side of this, so this is time derivative of temperature divided by temperature square. And the right-hand side is temperature square divided by Planck square times number of species. Now, the left-hand side of this equation is a parameter that measures departure from semi-classicality. Okay, if that parameter becomes order 1, you can forget about semi-classical theory. You can see simply, if this parameter becomes order 1, actually the black hole will radiate away the entire mass in one horizon time. And of course, that's nonsense. Semi-classical black hole cannot do that. Okay. Also, you can see that temperature will change faster than the temperature square. Okay. And so therefore, this immediately gives the bound on maximal temperature that the black hole can have. And the maximal temperature is m Planck divided by number of species. There is a very similar story in de Sitter. Okay, so in de Sitter, you can also ask this question. Okay, how high should be the de Sitter curvature before de Sitter, the thermal energy of species, produced species, overcomes the energy density of the cosmological constant that created de Sitter in the first place. Of course, this is absurd. This cannot happen. And this gives you bound. And you can see that this again becomes precisely at the curvature given by this bound on quantum gravity scale. So de Sitter of the smallest possible Hubble radius is given by this formula, square root from number of species divided by m Planck. Okay. Now, quantum breaking time gives a new meaning to this expression. And now we see explicitly what would happen. So if you violate the bound on species, if you have too many species in the theory, okay, which is this, given by this, if you have this number of species, then the quantum break time of de Sitter is shorter than the Hubble time, which is absurd because classical geometry, this means that you prepare classical geometry, and it just disappears less than in one Hubble time, okay? Obviously, this cannot happen. And so we see that what is happening from the point of view of quantum break time. So why this is important? Because all these conclusions, they are interrelated and they represent consistency checks of each other. And we see that the whole picture is absolutely, we see self-consistency in the picture. So now notice also that this bound implies that number of species that you can have in the theory has to be less than the number of de Sitter constituents, right? Okay, so that's also interesting. So it's like what theory tells us is that you cannot produce de Sitter with more constituents than the total number of species that you have in the theory. These species, they don't have to be gravitational. They can be whatever. I mean, hidden sectors, copies of the standard model, whatever you want, okay? So now we understand why theories with large number of species, they provide an exceptional opportunity for directly observing quantum gravity effects from the early universe. In the standard picture, that is impossible, okay? In the standard picture, those effects are too much suppressed. But with theories with large number of species, this delta is enhanced by number of species and actually can easily be observable, okay? In fact, the entire story of inflation may come from quantum gravitational effects. Density perturbations, for instance, can come from this type of quantum gravitational effects, okay? At the same time, if the number of species is sufficiently large, the standard fluctuations coming from inflaton field, they can be completely negligible. So the entire story may come from quantum gravity. Now, you can ask me, what is the bound, phenomenological bound on the number of species? And actually, the phenomenological bound on number of species is pretty mild. Okay, depends how you look at it, but the absolute bound on all possible species that we can have in the theory, in all the sectors, okay, in all the hidden sectors, and not only, of course, in the standard model, is actually of order 10 to the 32. So this is the bound from LHC experiment, Large Hadron Collider, and it comes from the fact that if number of species were much larger than this, Large Hadron Collider would see strong gravity effects. Because Large Hadron Collider is not seeing strong gravity effects, number of species, maximum number of species around this scale. Now, this number of species is highly motivated from a completely independent problem of the standard model, so-called hierarchy problem. Because see, if we have this number of species, then the cutoff is naturally lowered, and that's nice. We like theories with low cutoff because that explains, that makes life.
Sorry, what does it mean to say to see strong gravity effects? What are you ruling out?
No, for example,
you're assuming that you're seeing the standard model, deviations from the standard model.
Exactly. So, for example, you should see. I mean, there is a list of predictions that you should see once you hit the scale. For example, you should see quantum micro black holes. Okay, so strong resonances, gravitational resonances, and so on. And since we don't see those, we can safely, and this is absolute bound. So this is an absolute phenomenological bound. We can safely conclude that number of species in all possible sectors is less than 10 to the 32. But this gives a lot of room to go for inflationary model building, actually. And this gives plenty of possibilities to, for example, to have inflations with extremely low Hubble scales, okay? Because this number of species enhances quantum gravitational effects enormously, and that's very interesting. Okay? Now, in the remaining few minutes, I want to discuss the story of entanglement, okay, which is part of quantum breaking, obviously. And for de Sitter, this is okay for both black holes and de Sitter. This is something new, the aspect that I will discuss here. And it has to do with the understanding entanglement and understanding so-called Page's curve for de Sitter and black holes. Now, this concept of Page's curve, let me explain it. Probably you heard about it, but let me explain it. This was formulated in the context of a black hole. Now, the black hole, or let's say of radius r, has Hawking radiation, and there's the temperature, right? Hawking temperature, 1/r. Now, what Page argued is that the entanglement. Page argued that actually information carried by this radiation, you should be able, an observer, an outside observer, should be able to start resolving this information with order 1 rate after this time. That is essentially a half emission time of a black hole. So in other words, after black hole loses half of its mass, we get this Page's time. Now, notice that the Page's time coincides with quantum break time. Okay, so and this coincidence is not accidental. Of course, Page never discussed anything about quantum breaking or anything like that. Actually, Page was assuming that black hole evaporation at least he was allowing. I don't want to make I don't want to misrepresent anything, but I think at least he was allowing black hole evaporation to be self-similar. So now what is the story with Page's curve is that if you are in a semi-classical theory, you would naively say that okay, first of all, in semi-classical theory, I have a black hole, and black hole emits a particle, and there is an entanglement between outgoing particle and a black hole. And this entanglement grows because you emit more and more stuff, and this entanglement. And it looks like that in semi-classical theory, the entanglement goes indefinitely. Okay. Now, by the way, this is not surprising because in semi-classical theory, black hole mass is infinite because you are in the limit in which you have rigid geometry. And so it's not surprising that the entanglement grows. It's not that it grows indefinitely. The truth is that you don't see where it reaches the minimum, where it reaches the maximum. In any case, I mean, the main message that I will focus on from Page is that the entanglement must reach a maximum around Page's time. And this is considered to be a puzzle in semi-classical black hole treatment because, as I said, semi-classically, it looks like it increases indefinitely. Again, I don't think this is. I mean, I don't think this is inconsistency of semi-classical pictures. Semi-classical picture is perfectly consistent, but it has its limit, its domain of applicability. The problem here is not coming from the inconsistency of semi-classical picture, but it is coming from the use of semi-classical picture beyond the domain of applicability. Okay, semi-classical picture cannot be used beyond half evaporation time of a black hole. Okay, but anyway, this is the classic this is the standard, more or less standard formulation of the story. At least this is the question that I'm going to address. Okay. Now, of course, there is also a question which entanglement, but because in order to answer this, why this happens, we need a microscopic theory. These are the questions that cannot be answered in semi-classics. Now, in semi-classical picture, there is only one type of entanglement that you can define. This is because you are not resolving a black hole as a state, as a quantum state, as an internal corpuscular structure of a black hole. There's only one type of entanglement. This is entanglement between black hole and then outgoing quanta. So what happens, for instance, suppose black hole, imagine the black hole emits an electron. I don't know why I'm plotting electron with a wavy line, but anyway. So let's say we emit a particle with spin 1/2, which can have or any particle with two polarizations. Okay. So the black hole goes into a state black hole prime, but you are not resolving the state, and so you conclude that there is an entanglement, let's say, between black hole prime and the particle and the electron. So this is let me call it outer entanglement, so external entanglement. So in semi-classical picture, the only entanglement you can capture is external entanglement. Now, in order to understand what is going on with this state, black hole prime, you need a corpuscular theory, okay? And this theory reveals a very different picture. Now, this corpuscular theory of a black hole, we suggested actually in the same paper as the corpuscular theory for de Sitter, okay? My collaborators, Cesar Gomez and I. And it's very similar. Up until half breaking time, they behave very similarly. So again, it's a similar story. You think of a black hole as a state, as a saturated state of soft gravitons. Actually, you don't have to assume saturation. Saturation comes out. So if you, the key assumption is that black hole is a multi-graviton state of soft gravitons. Okay, so the bulk of this information physics of black hole is captured by this state. And then immediately discover that black hole is a saturated state, very similarly to de Sitter. Okay, so the number of constituents is equal to their inverse coupling and is equal to the entropy of the object. And so, therefore, the behavior up until quantum break time, behavior of black holes and de Sitter is very similar. So, therefore, you are already prepared. So instead, in case of black hole, we have Hawking radiation. In case of de Sitter, we have Gibbons-Hawking radiation. But the origin in our theory is very similar. So you have some kind of a multi-graviton state, a coherent state, or a composite, otherwise composite state. You can choose, which is saturated, and you can see that again at initial times you have Hawking radiation as a result of depletion, quantum depletion of this multi-graviton state, and you have this self-entanglement developed. So in other words, what happens is that when a black hole emits quanta, it becomes, what remains, it not only entangled with this quantum, but it's also self-entangled. And of course, self-entanglement has a maximum, because if you have an n particle state, that the entanglement of that n particle state cannot grow indefinitely. So this concept of self-entanglement is very important, because this contributes into the quantum breaking, and it also is the quantum is the component of the quantum clock that black holes have, and it is present in both for black holes and de Sitter. And again, it's very important that is fundamentally invisible in semi-classical picture. Okay. It has two engines. I don't have time to discuss those. If there will be questions, I'll be happy to explain. But there are two components. So in other words, there is an entanglement coming from the constituents of soft modes that compose the black hole, and also from the entanglement of what we call memory modes. These are the super soft modes that carry black hole entropy. And so there is this effect, which is very interesting. Unfortunately, I don't have time to discuss it. We call it memory burden, which is also contributing into the self-entanglement. Okay.
Sorry, Gia, may I interrupt you?
Yes, of course. Yes, absolutely.
Have I understood it correctly that the first type of entanglement is the entanglement due to release of the information? So it's it's an entanglement of the information released as a radiation, and the second is the entanglement within the object itself.
No, these are, so here I'm describing is these two bullets here. So the external entanglement is always there. Okay. But this is standard. Even in semi-classical picture, you do capture this external entanglement. The problem with semi-classical picture is that you don't resolve black hole. So therefore, you naively think that this entanglement grows indefinitely, and you don't see an inner clock for a black hole. That's the problem with semi-classical picture. So this entanglement between outgoing radiation and a black hole, that you can capture already in semi-classical picture. The problem with semi-classical picture is that you cannot capture the internal clock, okay, of the self-entanglement. So this is what I'm discussing. And there are two contributions into this self-entanglement. The one is from soft modes, and the other one is from super soft modes. Okay, so that's what I'm saying. Now, since I didn't, so I can talk more about this memory burden in the question section, happily, right? But these are both the components of the inner entanglement. Okay, all right. Now the thing is the following. So there is the message that the corpuscular picture brings you, tells you, and so immediately we were very happy long ago when we discussed this corpuscular picture, because we understood that this immediately explains phase. It actually explains phase in one line, that entanglement reaches the maximum period. Okay, so in our picture that's automatic. So there is a maximum entanglement reached around quantum breaking time, which coincides with Page's time. Okay. Again, it's very interesting that this quantum breaking time is derived from completely different considerations, right? I mean, from corpuscular picture, but it comes out to be Page's time. Okay. So, and there is not, in this sense, there is no difference between black hole and de Sitter. So the difference, the fundamental difference between black hole and de Sitter happens now. Of course, this self-entanglement, this story was never discussed for de Sitter, because for black holes, at least there was this semi-classical picture. There was this understanding of external entanglement, which I claim is only a minor part of this, not minor, but it's part of the story. But for De Sitter, this picture was never discussed because since self-entanglement was never discussed, okay? But they are very similar, black hole and De Sitter from this point of view. Entanglement grows in both, it reaches maximum, but the difference comes beyond quantum break time. And beyond quantum break time, black holes, so black holes beyond quantum break time, of course, is this, and this is also very important. This is brought by corpuscular picture. Corpuscular picture is telling us that beyond quantum break time, beyond after losing half of its mass, black hole decay can no longer be described by Hawking process, even approximately. Okay. At least there is no evidence that that type of rate continues. And there are some arguments why actually a black hole actually could slow down evaporation beyond half-life time, beyond not half-life time, beyond half emission time. So if after it loses half of its mass, now this has to be taken with a grain of salt, because now what we see, I can report what we see. Unfortunately, there is no computation beyond half-life time done in fully fledged quantum gravity. So all the computations were done in prototype models, including numerical computations, which have this similar information and entropy structure. Okay, and we see that in those prototype models, indeed there is a tendency of slowing down because there is this effect of memory burden. Okay. So, but that could be extremely interesting from the point of view of primordial black holes as dark matter, because it could tell us that actually the black holes that we thought they were gone long ago, the primordial black holes, in reality are still around because of because they got stabilized by memory burden. But I mean, slow down is not an important point for this particular discussion of entanglement. So sooner or later, the black hole, if you ask me, will decay. Okay, unless there is some conserved number that stabilizes it. But anyway, the black holes. What is important is that black holes, one way or another, they have a self-consistent life beyond quantum breaking time. The problem with De Sitter is that it doesn't have this life. So in other words, in quantum broken phase, De Sitter cannot exist. And so therefore, the De Sitter entanglement can grow maximally up until quantum breaking time, and then after that, De Sitter will not be a consistent. There will not be anything that you can call De Sitter or anything like that. Okay. So for consistency, the De Sitter should exit before quantum break time, as I said, and therefore, so the entanglement will grow up until the exit. An exit is, for example, by inflationary, for example, by inflaton clock, slow roll inflaton, or some other classical clock. So the De Sitter must exit from this phase. So there must be a graceful exit. And this is a fundamental difference between De Sitter and black holes. So there's, in other words, they are very similar in the sense that the entanglement reaches the maximum, but De Sitter doesn't seem to have a consistent lifetime beyond quantum breaking time. Black holes, they do, because black holes do not require. What's the reason? The reason is simple, because black holes do not require an external classical source in form of cosmological constant. Black holes are self-sustained objects, and they just continue consistently as they should. The problem with De Sitter is that it was created by an external classical source, and unless you remove this source, beyond quantum breaking time, the two become inconsistent, and this is the fundamental difference. Okay, so I'm done. Sorry, I think I'm a little bit over time. So the conclusions are basically okay. There are several conclusions, but let me just briefly. So what we are learning is that the S matrix formulation of gravity excludes the De Sitter vacua, irrespectively that they are stable or metastable. And this imposes upon us a corpuscular view. corpuscular view is that de Sitter is a saturated coherent state constructed on top of a S-matrix vacuum. And being a saturated state, it exhibits quantum breaking time. Beyond which, and this quantum breaking time, I discussed several physical meanings of this quantum breaking time. One is that the entanglement becomes maximal at that quantum breaking time. And beyond this quantum breaking time, de Sitter cannot continue. Now, this property is shared also by black holes, as I said, right? But for de Sitter, you must find a graceful exit. And then, because of this, there are quantum gravitational effects, imprints from the de Sitter phase, from the inflationary phase, which are given by this parameter, the ratio of the exit time to quantum break time. And these are enhanced by number of species. And so in theories with large number of species, actually this type of effects can be not only observable, they can be the major source of quantum effects in the universe, from the early universe, okay? And the bound, as I said, is 10 to the 32. And of course, for the present day cosmology, we predict that, what we predict is that lambda cannot be part of universe's energy budget, okay? Okay, then this raises a very interesting question. What is dark energy made of? And of course, precision analysis is very important. I brought some examples of the papers that are going back and revisiting this, but I'm not an observer. I can only say that the lambda cannot be part of the energy budget of the universe with our current understanding of quantum gravity. Okay, I'll finish here. I also had some couple of lines about effective S-matrix, but okay, I'll finish here. I'll stop here.
Thank you very much for a very
Thank you.
stimulating talk. And it's open to questions.
Yes. So instead of dark energy, let's consider dark matter. You said with a slowdown of primordial black hole decay, of course, the limits for primordial black hole as dark matter become weaker. Has that been studied?
Yes, very, very good. So thanks. Yes. So this idea about the trying to apply this slowdown to primordial ideas of primordial black holes is new. So we wrote paper with Lucas Eisenman, Marco Mitchell, and Sebastian Zell. And we have a section in that paper devoted to a preliminary analysis of some dark matter, some new windows of opportunity for primordial black holes as dark matter. It's a very interesting question. To my knowledge, so far it has not been studied in details, but it requires a complex study. And let me tell you why it requires a complex study, because so when the black hole so assuming that black hole evaporation slows down, the question you can ask now is that, okay, it emits less quanta, but it can still emit pretty energetic quanta, okay? Right? Because the energy of the quanta is most likely is again given by the typical frequency of the constituents and typical size of a black hole. And size of a black hole is not changing dramatically. It's only half of, I mean, it's of the same order as the initial size. So therefore, we should look for, so it's a combined study, not only now masses, but also the emitted quanta and how they distort diffuse gamma ray spectrum and this kind of stuff. So there is a bunch of extremely interesting astrophysical constraints on this type of emission products. Okay, and so this has to be studied in entire. You need complex of the analysis. So that's the only paper I know that addresses this. But yeah, it's by no means the analysis is complete there. So there are very interesting questions to be understood. So yeah.
Thank you.
Mm-hmm.
I have a question.
Yes, please.
You may know the answer. I want to pick up Denjo's remark on Rindler wedge. Okay?
Mhm.
In the Rindler wedge, one knows that the vacuum state restricted to the Rindler wedge is not a pure state. It is a KMS state. And one also knows that observations in the Rindler wedge cannot excite particle states, particle excitations on this restriction, because that is a non-local operation for the Rindler wedge. But you work entirely with pure states. I suppose it generalizes to mixed KMS states and so on, which is more appropriate in the de Sitter case, I think.
So right, yeah. Thanks very much for the question. So in other words, in the microscopic theory, we don't have to deal with mixed states. All the states are pure. So all the states that I'm discussing here, that I discussed in these talks, these are pure states, and this, including the entanglement that I discussed, is the entanglement generated in pure states. Okay, so these are pure states, but maximally entangled. So the philosophy here in corpuscular picture is the following: that the description by mixed states, or for example thermality of the states, this is an approximation which is better and better in semi-classical picture. But what microscopic theory gives you states which are always pure. But as you take the limit of semi-classical limit, for example, what would be the limit of Rindler in this case, right? The limit of Rindler in this case would be that I have to take n to infinity, and simultaneously I have to also take r large, because I'm in near horizon geometry of a black hole, okay, very close to horizon. So therefore, if you take this limit, what happens is that what you think of, there are certain set of pure states which become closer and closer to mixed states. So in other words, you see, if I, so let me explain in this way, right? So if I start with let's start with a system. Let's forget about black hole for a moment, right? Let's start with a system with a absolutely perfectly Hermitian Hamiltonian unitary system, okay, which has certain number of degrees of freedom, okay. This system has certain number of degrees of freedom, and if these degrees of freedom they satisfy certain requirements, for example, they have set of degrees of freedom that is nearly gapless, etc., etc. You can see that you can form states in this theory which are pure, but in order to distinguish them from thermal states, you will need to do measurements on an extremely long time scale. Okay, so therefore, this is the point here. The point here is that all the states that we are describing as thermal states, in reality, these are pure states which are, in that limit, infinitely close to thermal. Okay, so there is no contradiction there is no contradiction with this thing. Also, the spectrum, you can see it from the spectrum. In the same limit, the spectrum becomes exactly thermal. Okay. Now, of course, we understand that for a finite mass black hole, there is absolutely no way to have exactly thermal spectrum. It's simply impossible because of what I showed you here in this expression. I mean, this expression, right, is directly derived from Hawking with no extra assumptions. So you take Hawking's Stefan Boltzmann law of black hole, how black hole loses its mass, and the relation between temperature and the radius. With no extra assumption, you immediately derive this equation. Now, this equation immediately tells you that there is a limit to thermality. Why? Because thermal spectrum, the exact thermal states are the ones for which temperature is constant. Okay. If temperature changes, you always need to rethermalize your theory. And this always takes time because the degrees of freedom of your system are never infinitely strongly coupled, okay? So you always need time scale to rescatter your degrees of freedom and to readjust thermality. So therefore, in normal system with finite coupling, when temperature changes, the system cannot never be exactly thermal. But as you can see, the deviation from thermality is very small if the number of species is small. For example, let's take n equals 1 here, right? You see immediately that the measure of departure from thermality is 1 over n, or 1 divided by the entropy. For example, if I give you a mass of a black hole of an Earth mass, 1 centimeter size, and you ask, I see Hawking radiation from 1 centimeter black hole. How precise is the thermal description of the spectrum? It's precise with an accuracy of 1 part in 10 to the minus 60, in 10 to the 66. Okay, so the correction to thermality is 10 to the minus 66, which of course, for all the practical purposes, if you are observing black hole during a limited number of emissions, you can treat it as exactly thermal, but it's never exactly thermal. This is the point. Okay, now the Rindler case is a similar limit, except in that case you are also taking effectively radius very large, because you are in near horizon geometry from the Rindler. So in other words, the answer is that you can, in a corpuscular theory, you can consistently take the limit in which you recover exactly what you are saying.
Can I just clarify myself? Consider a free scalar field theory on Minkowski space. So it has a representation on a Fock space and pure states on the algebra consisting of all the observables on space-time. But there are theorems which say that in any local region, for example, the causal diamond or the Rindler wedge, there are no pure states. They are all KMS. Okay? This is some theorem.
No, I understand, but this doesn't contradict to what I'm saying.
So,
right?
Yeah, so I don't see how what you said now.
Yeah, because
I'm into the fact that there are no such states, pure states, on local algebras. Yeah.
Right. Yes. Exactly. No. Absolutely. Yeah. You're absolutely right. But this is what I'm trying to say. I'm saying that the Rindler. So this is precisely what I started with. I said if we are in GR, semi-classical GR, okay. So which means that I'm considering background classically, and then I'm doing quantum field theory on top of that background, okay. So then naively it looks like that arbitrary background, for example Rindler or de Sitter, I can treat as a vacuum, and I can build a theory on top of that vacuum, okay. But from the point of view of quantum gravity, this is not consistent, because quantum gravity tells me that I can only build theory if I can define S metrics on that vacuum, okay. Now, if vacuum has no globally defined time, there is no way to formulate quantum gravity on that background. As I said, other interactions like scalars, for instance, or gauge interactions, those you can. And for those interactions, there is a consistent limit that you can take from corpuscular theory, okay? Now, of course, I have not done all the examples, but that doesn't matter. It's a matter of concept. What I'm saying is that for those cases, if you are willing to decouple quantum gravity and maintain, let's say, some scalar theory to be self-interacting, for example, lambda phi to the fourth. People have been discussing lambda phi to the fourth within the Sitter space, and that's perfectly consistent with what I'm saying, because you can take de Sitter as a vacuum, and on top of that, discuss lambda phi to the fourth. And then you recover what you are saying. So in other words, you recover that. In that case, you can define your theory. You can define as states as thermal and mixed states, and that will be consistent, okay? Because that corresponds to the limit of the corpuscular description in which that is possible. But that is what I'm saying is that is impossible if you keep finite time Planck. So what I'm saying is that there is no such thing as Rindler space, or there is no such thing as the Sitter space geometry in a theory, in a consistent S matrix theory with finite Planck mass. All those spaces are approximations, okay? So, and this is very important. This is the key concept of this corpuscular resolution of geometry, okay? So there is no self-consistent Rindler space-time for finite Planck mass as a vacuum, okay? So this is the point. It only exists as a consistent space-time in the limit in which you take Newton's constant to 0 and the energy that creates the horizon to infinity, so that you keep geometry fixed. It's only in that limit. But in that limit, quantum gravity decouples, and what you are saying, everything you are saying is absolutely correct. So obviously, I mean, semi-classics works within the domain of applicability. And there is absolutely no problem with defining mixed states and thermal states once you work in semi-classical approximation. But again, I mean, it's very important. Sorry, I keep repeating myself, but I'm really obsessed with this because it is very important to understand that every time we work in semi-classical approximation, we're implicitly taking the limit in which Newton's constant is 0. Okay, and we are fixing geometry, and nowhere the Newton's constant enters in that geometry. Okay, right? I mean, if you are, so yeah. Yes.
Thanks very much. I had to think about it, but it was a very stimulating talk.
Thank you very much. No, the question that you are asking is absolutely important, and this is, and sorry, I think I repeated my answer 3 times or something. Sorry.
Can you comment on anti-de Sitter space?
Yeah, anti-de Sitter is very interesting case. Now, first of all, for anti-de Sitter, there is no inconsistency of this sort, and actually that also is clearly seen from ADS-CFT correspondence. So in anti-de Sitter, we have formulation of anti-de Sitter, a consistent formulation, consistent quantum formulation in terms of within ADS-CFT correspondence. So there are no inconsistency arises. Okay, so therefore there is no nothing that I said here about quantum breaking stuff would exclude anti-de Sitter. And
but
actually, this is also
you should be able to treat it in a similar way in a corpuscular way.
Yeah, that's a very good question. So yeah, we had some. Yeah, we speculated in the very first paper. We said, okay, can we also treat anti-de Sitter in a corpuscular way? Okay. Now, there is one caveat there. The caveat is that you see, as I said, for de Sitter or a black hole, we don't have a choice because S matrix imposes upon us corpuscular resolution. Okay. Now, since in anti-de Sitter you don't have any problem with S matrix, it's unclear whether this corpuscular resolution is necessarily has to be imposed upon us. Okay, so there is this very important difference between de Sitter, black hole, and anti-de Sitter.
But so I can also take a near horizon limit
true, absolutely. But what I'm saying is that at least there is no pressure from the S matrix point of view to resolve anti-de Sitter in a corpuscular way. Nevertheless, we tried to ask this question. We said, could we think of anti-de Sitter also as some kind of a saturated state, critical state of gravitons constructed on top of Minkowski, let's say, okay? I mean, we didn't succeed fully, okay? But there is one interesting observation. I don't know what to make of that observation, but there is one interesting observation. So it looks like that if you assume this, if you make this assumption and you naively count, again, I mean, this has to be taken with a grain of salt. If you naively count the number of constituents of the anti-de Sitter space, you recover the central charge of CFT. Okay, so somehow there is this coincidence. I don't know what really to make of it. But again, what I'm saying is that there is an important difference because in anti-de Sitter space there is no urgency to do anything like that because it's perfectly fine with S matrix and with quantum gravity. Because of this power of ADS-CFT. Okay, so therefore that's the way maybe the theory is telling us that we should not worry about anti-de Sitter space.
Other questions? I don't want to dominate this.
Can I ask quickly?
Brian, go ahead, Brian.
You chose a slicing where the scale factor was the exponential of time.
Yeah.
There's another slicing where the scale factor is a hyperbolic cosine of time.
That's right. Yeah.
Are the results affected by using different slices? What would
no, not really. Because no, not really. Because I just use this slicing because it's sort of Friedman, Lemaitre, Friedman, Robertson, Walker friendly. Yeah, that was the only reason. And this.
But they do seem to be different because with the cosine formulation, you have a symmetry sending t to minus t.
No, sure.
And you don't have that with the exponential slicing.
No, sure. Of course, there's also, for example, even static patch. For example, you can also introduce de Sitter in a static patch and in many different slicings. Yes, No, that doesn't make much difference from the point of view of this time. Of course, what is important, obviously, because I mean, slicing is like choice of gauge, and every time we choose a gauge, of course, is also a matter of convenience. And corpuscular resolution that is convenient in one gauge may not be convenient in the other gauge, obviously, because gravitons themselves they exhibit gauge redundancy, obviously. So yeah, from their point of view, of course, some of the slicings, certain effects may be hidden in some of the slicings, but that's also true classically. For example, if I naively look at the static patch of the sitter, I may conclude that everything is static there, but of course, I mean, of course, that's not the case. So yeah, I mean, there could be subtleties related with the choice of slicing exactly in the same way as there are subtleties related with the choice of gauge if you want to do corpuscular resolution. That's absolutely correct, yeah. But the statements like quantum break time and these kind of things are invariant. So those those are slicing independent because they are gauge independent. They just come from the fact that the observables that you see observables how they depart from how expectation values depart from the from the classical ones, etc. So yeah, but of course, I mean, these are the slicing and gauge choices are technical things that we have to watch, of course, all the time. But by the way, that's also true for gravitational wave. Gravitational wave also we can think of it classically, but in reality, it's a coherent state of gravitons, and of course, there is less surprising that it's a coherent state of gravitons, but still, I mean, these issues of also appear there. So.
Other questions? If there are no other questions, I'll stop the recording and we can be less formal. Okay.
Okay.